Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. The glacier ice impact hypothesis, published in 2017, proposes that an extraterrestrial impact on the Laurentide Ice Sheet ejected pieces of glacier ice in ballistic trajectories, and that the oblique impact of the ice boulders created inclined conical cavities that transformed into shallow elliptical depressions known as the Carolina Bays and the Nebraska rainwater basins. Both of these geological features have similar geometry, and they occur on saturated ground that was liquefied by the energetic impacts of the glacier ice boulders. However, the ice projectiles also fell on a variety of terrains, including marshes, rivers, and mountains. This video examines the traces left by the ice impacts on a variety of terrains. Toward the end of the Pleistocene epoch, North America was covered with a layer of ice more than 2 kilometers thick. The Laurentide Ice Sheet covered most of Canada and the northern portion of the United States. Mastodons and other large animals inhabited the land, and the Clovis people hunted them with weapons fitted with finely crafted arrowheads. Approximately 12,900 years ago, an asteroid or comet approached the Earth at a speed from 17 to 45 kilometers per second. The extraterrestrial object started to glow from the friction of the Earth's atmosphere. The object became incandescent, and its radiant heat started fires on the forests under its path. The projectile traversed the atmosphere in less than 1 minute and started a sequence of events that changed Earth's history. The impact on the Laurentide Ice Sheet fractured the ice, and the excavation of the crater ejected millions of huge ice boulders. The heat from the impact created a plume of steam that propelled the ejected ice boulders with great speed. The ice boulders in the Ejecta curtain were launched in suborbital space flights with a range of 1,500 kilometers from the impact site. Approximately 1.5 trillion cubic meters of ice were ejected by the extraterrestrial impact at speeds from 3 to 4 kilometers per second. Depending on their size, the ice boulders had kinetic energies of 13 kilotons to 3 megatons of TNT. The saturation bombardment by the ice boulders killed the megafauna and the Clovis people. The great density of elliptical scars along the Atlantic coast proved that there was no place to hide from the impacts of the giant ice boulders. We know that the ice impacts liquefied the soil and created inclined conical cavities because the resulting bays have a mathematically elliptical geometry that corresponds to conic sections. Well-preserved Carolina bays are perfect ellipses, but many of them have been deformed by terrestrial processes. Impacts on ground that did not have enough depth of unconsolidated ground to allow the formation of conical cavities produced circular bays such as those found in the Delmarva Peninsula. Impacts on inclined terrain caused the liquefied soil to flow downhill after the formation of the conical cavity. The uphill side of these Carolina bays was distorted by the mud flow. The impacts of ice boulders on marshes and wetlands produced splashes of sandy soil that created deposits around the margins of the elliptical bays. The bays in Jones Lake State Park, North Carolina, have scalloped sandy fringes that are highlighted in this image. Impacts on rivers created tsunamis that put sandy debris on bays that had just formed. In 2010, Brooks, Taylor, and Ivester described Big Bay as being covered by an Aeolian sand sheet, but notice that the small bay at the top of the image, circled in red, is not covered by the sand sheet. What could have prevented the wind from depositing sand on the small bay? The geological law of superposition offers an explanation which indicates that Big Bay formed first. The bay was then covered by a sand sheet deposited by a tsunami from an impact on the watery river, and finally, a small bay formed on top of the sand sheet. Here we can see that two big ice boulders created Big Bay and its lower companion bay. Seconds later, another big boulder impacted the watery river. The splash from the impact created a tsunami that dredged the sandy deposits that had accumulated along the river bank for 74,000 years. The sandy soil was carried inland by the tsunami for 6 kilometers, and a sand sheet was deposited on a portion of Big Bay and its companion bay. A few seconds later, a small ice boulder came down to create a small bay on top of the sand sheet. Chevron sand dunes deposited at the margins of a body of water are typical evidence of a tsunami. This image shows Kelly Bay in South Carolina with sandy incursions. Like the example of Big Bay, the upper chevron on Kelly Bay has the crater of a small impact. This geological formation suggests that after Kelly Bay formed, a tsunami from an impact on the Little PD River deposited 2 chevron dunes, and subsequently a small ice boulder produced a crater on the chevron marked with a circle. First, impacts of glacier ice boulders created Kelly Bay and other neighboring bays. Next, an impact on the Little PD River created a tsunami that dredged sand from the riverbed. The water advanced over the bay, carrying the dredged sand. When the water receded, the chevron sand dunes overlaid Kelly Bay. Finally, a small late impact created a small bay on top of the northern chevron sand dune. Chevron dunes from tsunamis are found in many parts of the world. Here are some examples from Madagascar and Mozambique. The mechanism of formation is the same as illustrated for Big Bay and Kelly Bay. A wave of water dredges sandy material near the shore and carries it to higher terrain. When the water drains away, it leaves sandy deposits with the typical scallop or chevron shapes. The extraterrestrial impact on the Laurentide Ice Sheet ejected giant ice boulders. The secondary impacts of these ice boulders had enough energy to cause landslides on unstable ground. Some of the largest known landslides in North America are found in Montgomery and Craig Counties, Virginia, in the Blacksburg-White Ranger districts of the Jefferson National Forest. One of the landslides is more than 3 miles long. The ancient giant landslides extend for more than 20 miles along the eastern slope of Sinking Creek Mountain. Evidence suggests that the landslide movement occurred between about 10,000 and 25,000 years ago during the Pleistocene Ice Age within the time frame of the extraterrestrial impact. The ice boulders that hit solid ground disintegrated explosively with energies equivalent to 13 kilotons to 3 megatons of TNT. That energy is equivalent to earthquakes of magnitude 6.0 to 7.54. Here is another example of a landslide that has been dated to the time of the extraterrestrial impact. Jacobson et al. Describe a landslide at Pendleton County in West Virginia at 12,920 BP that corresponds to the time of the Younger Dryas onset. These landslides are circumstantial evidence of the extraterrestrial impact, but it is the type of effect that would be expected from a hailstorm of massive ice boulders. This presentation has considered the effect that the impacts of glacier ice boulders had on different terrain types. Impacts on saturated ground produced elliptical bays. Impacts on sandy soil that could not be liquefied produced circular bays. Impacts on hills produced bays distorted by mud flow. Impacts on marshes produced sandy splashes around the base. Impacts on rivers created tsunamis that formed chevron dunes on adjacent bays. Impacts on mountains triggered landslides. Many ice boulders shattered upon striking hard ground and left no trace. Now that we know that the eastern part of the United States was bombarded by a barrage of huge glacier ice boulders, we have to look at the geology of the region in a way that considers impact cratering with subsequent modifications by terrestrial processes. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.